taken you through.
So can you please start the recording?
Yes, yes, I have started.
Yes. So, Professor Shorangshu has really taken you through the beta C features, the whole class features, hierarchy, templates, exceptions, all of that. Now, the question is, how do we put all these, features together to actually provide solution? So the approach that we will follow alongside the discussions of so-called theoretical aspects of software engineering is to develop some relatively small assignments which go through the same processes that we are talking about. So the first of that is to put together all your learning to building three data types, of which fraction you may have seen in parts and bits and pieces through the examples that are already discussed. I'm not sure. Then we'll have a limited size integer to implement and a polynomial to implement. Right? So this is more or less the outline of the assignment. So first, let me just recap on the data types. So data types in C++ are used to specify the type of the data, its size, its operations, its memory layout, and so on and so forth. And as you have learned, there are three categories of data types broadly. One are the built-in or primitive data types, like char, int, float, double, etc. They are predefined. They can be directly used in the program, and they have their built-in operations. Apart from this, we have void, we have bool data type as well in C++. Then we have a set of derived data types. That is, using these data types and using some constructs of the program, new data types get defined. So the derived types, which is a notion coming from C directly, include arrays. You can have array of integer, array of float, and so on. Functions. Function is a data type which takes 0 or more parameters of certain given types and returns a result of certain type or returns nothing, void. Then you have pointers, and in C++ you have references. Now, in addition to that, now we have user-defined data types like structure, union, enumerations, and classes. Of these structures, union and enumerations were there in C as well, but there only you could define an aggregate of data. There was no encapsulation, there was no functionality operation that could be provided. But now you can do that in C++ in terms of structures, unions, and classes, and enumerations, which are mere listing of enumerated values, is now also a type, a separate user-defined type in C++ 11. C++ 03 still treats enumeration as a special case of integer. But okay, so these are the different types. So built-in types and derived types have their own semantics. User-defined types can be given their semantics. And the two mechanisms that help us in defining semantics of user-defined types, one and the most important one is operator overloading, which help us build complete algebra for the user-defined types, much in the same way that built-in types work. Like I can have a complex type, I think, several examples of complex types were taken, so that you can directly add, subtract, multiply, divide, compare, etc. of two complex numbers without using a separate member function name. You can just overload the operation. Same thing you can do for fractions, you can do for matrix, even vectors, set types, and so on. And for all of these, you can also overload the streaming operators. There is a typo in the right operator symbol. We'll correct that. Now, in this context, let us take the problem that we want to do. We want to define a fraction data type as a user-defined data type. Right? So we intend to design a fraction which will behave like a built-in type, say like int, right? Kind of the way I can use int, I should be able to use a fraction. So in terms of engineering, the broad tasks that we will have to define, that we will have to embark on, include we have to have a clear concept of the fraction. We have to make a clear statement about it, which subsequently we will say is a specification. We'll talk more about that, but just get introduced to these terms. Then you have to identify a representation of the fraction object, because we want to represent that as a data type. We have to identify the properties and assertions that are applicable to all objects, so that we can put that in. Identify the operations from that. Once we understand the operations, we have to choose appropriate operators to overload. For example, if we have to add two fractions, we will choose to overload operator plus. To output stream a fraction, we will use operator output stream and so on. And why will we do that? We have to make sure that we do not break the natural semantics for the operators, because the whole idea of user-defined types or design of user-defined types and overloading is that it should be very easily understandable to anyone. So the idea is like you should not overload operator plus to mean a product of two functions. I mean, functionality wise, you can always write that, but that's not something that you should ever try to do. Right? So while it is possible to design and implement the UDT in one go, maybe if you have the expertise and the intelligence to do that, usually it is always better to go with iterative refinement. That is, make a design from the specification, make a design, implement that, test that, and then refine and repeat that process. Right? So that's the whole idea that we are trying to inculcate. So the first thing is naturally the concept that we are trying to implement. So you have to define the concept in a very crisp manner so that we can have a clear specification of what we want to do. Okay. So what is a fraction? We all know fraction is a notation for numbers of the form p by q, where p and q are integers. So these are fractions. You have to be clear in terms of specification that if you define fraction just like that, then the representation will be non-unique. 2 by 3 is same as 4 by 6, 8 by 12, and you cannot work with a non-unique representation. So you have to uniquify the representation. So to uniquify the representation, we put two restrictions on the fraction being a ratio of two integers. We say that q must be positive, because out of the two integers to represent negative fractions, we need one of them to be negative. So we say that we restrict that q must be positive, and p and q must be mutually prime. That is, their greatest common divisor must be 1. So out of 2 by 3, 4 by 6, 8 by 12, and so on, only 2 by 3 would be eligible because in 2 by 3 the GCD is 1. In 4 by 6 the GCD is 2, which is not permissible. Similarly, if you have to represent minus 2 by 3, you will not allow 2 by minus 3, rather you will allow only minus 2 by 3. So if you put these two restrictions, then the integers become unique, and that is what you know is a rational numbers. Further, a fraction is proper if its absolute value is less than 1. It is improper otherwise. And improper fractions can be written in mixed fraction format. That is, if I have 17 by 3, I can write it as 5 whole number, maximum whole number within that, and 2 by 3. Right? So this is the basic notion. This is the basic concept that we have. So given that, you can consider here, since it is mathematical, so it is possible to provide a concrete definition. So this is a concrete definition of P by Q. P and Q are mutually prime, Q greater than 0, P belongs to the set of integers, Q belongs to the set of natural numbers, P is called the numerator, Q is called the denominator. And if the GCD is not less than 1, then the fraction is irreduced, and it can be reduced by dividing the numerator and the denominator by the GCD. We know this. Now, what are the operations? Naturally, one operation that immediately crops up is that of reduction. So if I have given two numbers P and Q, then I can reduce it in my reduced fraction form by dividing by the GCD. If Q is negative, then I can flip the sign of numerator and denominator both. If P is 0, I force that Q is 1. Otherwise, 0 by 1, 0 by 2, 0 by 3, all are in the same thing. So I uniquify by saying that if P is 0, then Q is 1. And obviously, if Q is 0, then the fraction cannot be defined. It's an undefined one. So this is a reduction operation on any pair of numbers P and Q. So that given P and Q, I can make them to represent a fraction. Then we have the standard addition rule, subtraction rule, multiplication rule, and so on, which I will not go through in detail, because you all will know that the addition rule is only important. And here we use the well-known identity that GCD of two numbers multiplied by the LCM of two numbers is equal to the product of the two numbers. So with that, this is the addition. Subtraction would be simply redefined in terms of addition by using the negative of the second fraction, multiplication, division, modulo, or simple. So these are the operations. We have a few rules of fraction also. There is a rule of invertendo, which interchanges P and Q. Alternando does not have much consequence in our design. Then you have the rule of componendo, which is basically adding 1 to the fraction. And dividendo, which is basically subtracting 1 from the fraction. So they can be thought of as prefix or postfix increment or decrement operators. So given this, the specification of the fraction UDT is, now the representation here is,
Sir?
Yes, please.
Sir, I had a doubt in the last slide, sir.
Yes.
Sir, we are defining a unique definition for function for the fractions. So, sir, P upon Q is equal to R upon S will give the same as P is equal to R and Q is equal to S.
No, that is if you once you have unified. These rules are from mathematics.
Okay, sir.
These rules are from mathematics that you can, if you have two fractions which are equal, then you can invert them, and the equality is maintained.
Yes,
so I'm just using that mathematical rule to define. So in blue, if you see, that is the mathematical rule, right? You open up any textbook of middle school, you will find these rules. And in red, I have marked what is the operation that I identify. So just try to understand the process. I first introduce the concept as a notion. Then I'm trying to identify that as a data type, what are the operations it should do. So some operations are simply borrowed from integer type, and we know that they apply to fractions, so we have defined. And some more are specially defined for the fractions in mathematics. So I have just identified that. Right? So this will, at the end, give us the mapping between the standard operators that we have in C++ and what it means in terms of the fraction. And only then I'll be able to specify, right? Unless I have a meaning, exclamation, what does it mean? Right? Exclamation in say Boolean terms, it means negation. Right? In integer terms, it means that you interpret that integer as a Boolean bool, and then you negate that truth value. So it has a sense of, kind of going from one form to the other. So in that sense, I'm saying that I can use exclamation to just invert a function. That is, change P and Q. Got it? Okay. So the specification, the first part of the specification is simple. So I say fraction is a class, and it has to have two data members, numerator and denominator. Now, I could have defined them as int, but I'm trying to do something a little bit more generalized, because you have learned how to have generalized types. So I'm saying that the fraction is parameterized by a template parameter t, so that the numerator and denominator could be of any integral type. So I can have fraction of ints, I can have fraction of char, I can have fraction of long. I can have fraction of any other type which behaves like the integral type. Right? So I parameterize that with minus equal to this kind of things I should be able to do with fraction, because I can do them with int. I should be able to compare two fractions, less equal, all of that. And I should be able to do read write IO operations. Okay? So this is the broad specification. One in terms of the data representation, and one in terms of the operations that I can do. In addition, I could do some extended operations like invert. I just talked about invert, and conversion to double, which is natural. So any fraction should be convertible to double. So I should have a conversion to double operator as well. So this is these middle 2 points are basically the specification from where I will derive the interface part of the design. Because if you see, the second bullet and the third bullet define all the different operations that a user can do with this fraction utility class once this is created. The first primarily is a part of the implementation. Right, I could have implemented in this, obviously is obvious implementation, but I could have implemented in some other way also. So if I keep that, so this is the first point is basically in my moving from my specification to design will not be a part of the interface, but it will be a part of the implementation of the class. Similarly, in the fourth point, I identify that there are few, functionalities that I will very frequently need. So it is good to have them as a part of this class, but as a part of implementation, not as a part of interface. So you need to do a GCD, you need to do an LCM, right? And you need to do reduction of a fraction, because we have seen that the fractions can be in reduced form. And for example, when I create a fraction, I may create a fraction with numerator 3 and denominator 6. My internal representation for that should become 1 by 1 and 2, right? So that reduction is involved. And irreduced fraction will get generated when I do arithmetic operations quite easily. So I'll reduce things every time. Right? So the first and the fourth are parts of the basic implementation, and the first, second, and the third are the parts of the basic interface of the fraction utility. And this is what I say is a specification. So what we are saying is we want an utility which will do all this, which will have all this. Okay. So based on this, the actual task of the assignment will start. So you have to now design a complete interface for fraction t, where t is the underlying type on which the fraction is being defined. And in that process, you have to appropriately overload operators wherever applicable, wherever available. So when we talk about the design of the interface, that necessarily means, if I go back one slide, say, so you have to give what is the signature of the default constructor. Will there be a default constructor? What will be the parametric constructors? Will there be a copy constructor? So you put down the signatures of each one of these with proper identification of the operator being overloaded, and that will give you the total design interface along with the parts of implementation that we have already discussed. Second would be to implement the UDT, that is basically write the function body for every member function that you have defined, or deciding on whether the member function should be static or it should be non-static. If it is non-static, should it be a constant member function? Should some function be friend, that is actually global but in the namespace of the fraction type, and so on and so forth. So implementation will take these definitions from the interface and implement the respective functions. Right? So once that class is ready, now we will be able to write the test application. So we have the specification. From that, we have gone to the design, which is primarily the design of the interface and the design of the implementation in terms of data members and additional functions, additional member functions that we might need. Then the implementation, which is actually writing the code for the member functions, static member functions, friend functions, and so on. And once this is now ready, now I have to see that this actually behaves like an integer. So for every function, every member function, every operation that we have defined for fraction t, we have to write a test. That we have to test that it is getting properly constructed, it is getting properly reduced, it is getting properly added, it is getting properly compared, it can be read in the format in which you wanted, it can be written in the format you wanted, and so on. So you will write an application, so a test function, which will treat with all these different forms of fractions and their operations and perform the test and write out the result for your understanding, or print messages for your understanding. As we'll see, it is customary to classify the tests in at least in two groups. One is tests that you expect to pass. If I construct a fraction with 2 and 3, then I should get a fraction 2 by 3. So I write that as a pass test. At the same time, there are tests which you expect to fail. For example, if I try to construct a fraction with 2 and 0, then it should fail. It should not be possible to construct that. Or if I have a fraction 0 and I'm trying to divide another fraction by this fraction 0, then it should fail. Right? So you have a set of pass tests in a test application. You have a set of fail tests in a test application. These are what we will call unit tests, because each test is intended towards testing one particular interface, one particular operation that you have defined and implemented for the fraction unit. And finally, you would like to do some complex mixed test. For example, you have addition, subtraction, multiplication, division, inversion, comparison. So you want to say that F1 plus F2 times F3 minus F5 times F6, the whole thing divided by F9. What should it be? Now this entire thing should also compile, execute, and give you proper results. So that is the meaning of the mixed test or complex test and so on. Right? So this is what the basic task, and you should organize your code properly. That is, the definition of the class must be written in the header. You may implement small member functions within the class itself, or you can have a implementation source file for the class where you implement them. And you will certainly have source files for the applications. So use a proper organization of the code. We are not asking for separate documentation of what you have done. So you should nicely comment the class definition, the implementation codes, the test application, to highlight the design choices you have made, the implementation considerations you have given, possible errors that it might have, if there's some caveat and so on. Right? So this is the task. This is the notion of the fraction unity and the task to design it. Let me stop and ask if there are questions. Then otherwise I'll go on to discussing the other two utilities.
Sir?
Yes.
Sir, it is written that GCD and LCM should also be included as a functionality. Are they GCD and LCM of the fractions or else of just two integers?
See, GCD, if you have to reduce a fraction.
Yeah, we need
right?
GCD.
GCD, right? So it is a GCD of two integers.
Okay.
If you had to add two fractions, you need LCM of two numbers.
Okay.
Right?
Yeah.
So these are typically called convenience functions, or support functions, utility functions, which you provide. Now, it may be possible to have them from the standard library, and that could also be used. I'm not saying it cannot be used, but you'll have to see that here we are asking for designing a fraction class with an underlying type T. Right? So if you want to use a GCD from a library, then you have to see that that GCD code is written in an appropriate way so that your intended types T can be used for that GCD. Are you getting my point? That is,
yes, sir.
The numbers are fine, but when it comes to actual, putting it in the code, T could be int, it could be long. Now, if you have a library function of GCD which finds GCD of 2 int, that will serve when T is int, but that will not serve when T is long, or that will not serve when T is something that you have defined. Right? It is not necessarily that integral types will all be built-in types. Right? So that's the reason that it is better to think of that you write your own GCD and LCM, which are parameterized in the same way with the type variable T, and include them as a part of the class. But you certainly do not want somebody to use that GCD and LCM function as a functionality of the fraction class, because fraction does not have a GCD functionality. So you will certainly manage that by, as you have learned through the access specifier, that you make them private. Like your data members also you make private. Does that clarify?
Yes, sir. Yeah.
Any other question? Is this concept, approach, and the assignment clear? Assignment on the fraction utility part. Good. So let me go ahead and introduce the other two concepts. Now it will be easier. Please. Are you asking? Yes.
Yes, sir, in the template thing, when the template is specified as a car, so in that case, do we implement it as we convert it to an integer and then store it as
No.
a fraction? Or
No.
we just make it such that only 0 to 9 of the cards will be converted to the integers and then?
No. Char is an integral type. Char is an integral type. It is 0 to 255.
Okay, so we will consider that.
You are thinking of char as the numeral representation of in char type. 0 to 9 are numeral are representation of your numeric symbols as a character. But char, besides that, char is an integral type. It's a signed integral type. Unsigned char is an unsigned integral type. Its only difference is that it has a different size than the int. If int is 32-bit, but unsigned char is guaranteed to be 1 byte, 8 bits. Right. So the conversion is not to be done because you do not know what t is. You do not know whether t can be converted to it. T may not be convertible to it. Right. T may have the operations, all operations that int does, but t may not be convertible to it. It may not have an int representation. Are you getting me?
Yes, sir. Understood, sir.
As long as t can be added, subtracted, multiplied, divided, taken remainder of, and so on, it is eligible to be the type of P and type of Q in a P by Q form. Right.
Okay.
So
okay.
Right. So I mean, let me talk about the next data type. You will immediately understand why am I saying this.
Okay.
Right. Then again, you ask the question. So the next data type that I want you to implement is I call int n. So you know the data type int, which is a signed integer and represented a given number of bits, which is machine dependent, which you cannot control. 8-bit, 16-bit, 32-bit, even up to 128-bit. And it can represent numbers from the largest being int max to int min. So it basically means in 32 bits, it means int max is 2 to the power 31 minus 1 and int min is minus 2 to the power 31. Int max is 1 less because 0 is counted on the positive side. Right? So if you just try it out on a 32-bit machine, this is what you'll see. Int max is this number, which is 2 to the power 31 minus 1. This is minus 2 to the power 31. And if you add, this is interesting. Please note that. If you add 1 to int max, it becomes int min. If you add 1 to int max, it becomes int min. So it wraps around. Similarly, if you subtract 1 from int min, it becomes int max. So it's not only is a linear scale, but since the representation is finite, the Boolean arithmetic unit that you have in the hardware, in terms of the bit operations, realizes it. I mean, it turns out that if you overflow on the maximum side, you start from the minimum value. And if you overflow on the minimum side, you start on the maximum value. Right? So this is the characteristic. That's why I'm saying understanding it, the notion. Right? We understand int always as a whole number, can be positive, negative, can be added, subtracted, but the added connotation is it has a wraparound. It has a finite range in which it can be represented. Right? So that's the notion. Now, based on that notion, what we want to do, we want to design a UDT which will behave like int, but will have capital N number of bits. Capital N is greater than 0. So clearly the maximum that you can represent in this type would be 2 to the power n minus 1 minus 1, and the minimum is minus 2 to the power n minus 1, as you can easily figure out, and it will have that wraparound. So again, we want to make a clear statement of the concept, identify the representation, assertions, operations of this type, so on and so forth. So coming to the more concrete of the int type, it has capital N bits. It has a range from minus 2 to the power n minus 1 to 2 to the power n minus 1 minus 1. And beyond this range, it wraps around. So you have the basic arithmetic that maxint plus 1 is minint, and minint minus 1 is maxint. So if you take a value 4 for the number of bits, then your range will work out to be minus 8 to 7. Clear. And you have maxint 7 plus 1 is minus 8, wraps around. 8 minus 1 is 7, wraps around. And if you do just simple minus 8, it is minus 8. Right? Minus of minint is minint. That is because you have total even number of numbers represented. Of that, 1 is 0. Right? So maxint to minus maxint have their negatives properly mapped. But if you have the minint, it has no other representation. So minint turns out to be that if you negate minint, it turns out to be minus of minint. When you do more of the computer organization, arithmetic and all, I do not know if you have done that. You will know how hardware actually handles this. So this is the notion. I mean, we just need this notion. So not how hardware does it. So the operations are certainly you have two limits. The negation is minus a is a if a is same as minint, otherwise it is minus a. And if I add or if I add, then if I exit maxint, then I'll wrap around. What is wrapping around? Wrapping around is reducing the sum by 2 to the power n. That is, if n is 4, then max int is 7. So if my result exceeds 7, say I'm adding 5 with 6, the result should have been 11, but it exceeds 7. So it exceeds 7 by 4. Right? So it becomes minus 8, minus 7, minus 6, minus 5. Right? So that is the result it will come from. So what is minus 5? So it's basically when you wrap around from maxint to minint, you are reducing the actual value by 2 to the power n. Similarly, when you wrap around from minint to maxint, you are actually increasing the value by 2 to the power n. So in terms of your real algebra, this is what your addition for int is. Subtraction is simple. You can just negate and add, and you'll get subtraction. Multiplication, division, and modulus I have not defined. I've left it as an exercise for you. So based on this, what is the specification? Clearly, the representation of int n is a template which has int as your basic underlying type. You could define any other underlying type also. And you have a number of bits parameter, which is an unsigned int parameter, say defaulted by 4. Now, why do we have the underlying type as also a template variable? Because if I want to have a number of bits which is more than the number of bits available in int, suppose I want to have a 36-bit int, I cannot do with just underlying type being int, because that itself will overflow with 32 bits. So I need to have an underlying type which is long. And then in long, I can define the number of bits to be 36. So in this way, I can go up to the maximum number of bits that are representable in the hardware of the system. Right? So that is my maximum. So it is important to note that n has to be less than equal to size of t. So I have a, it should support the operations of int. I have not listed because operations of int are known. And additionally, you may support two constants, max int and min int, as your normal int type does, so that it becomes easy to work with that. Okay. So with that, the task is the same. Design the, so this is the specification. So based on that, you have to design the interface, all different operations, overloads of operators, other member functions, static, friend, all that, and then implement those functions in terms of the class intent, and then write test applications for the pass and fail tests. Right. For example, if I have underlying type as char, and I'm specifying n, which is 10, and your char has a representation of 8 bits in the system, then your code should refuse to compile. Okay? So that's so you can easily see that just referring to the discussions we were having just before I started discussing this type, is that now int n is an integral type. So I can have a fraction of int n. So I can have a fraction where the numerator and the denominator are represented in 4 bits, they wrap around in 4 bits, but they behave, that ratio behaves like a fraction. Right? Let me get back to ask if there are specific questions. Is this clear? Is this intent data type clear? Any questions on the specification and the task? No, you all are smart students and good. Good to talk with such smart bunch of people. The third is a polynomial. All of you know what a polynomial is, but just again, in the same style, let us define the concept. The concept certainly is a polynomial ax of variable x having degree n, has n plus 1 coefficients, which is written by a0 plus a1x in this way, and all the summation notation. So if I want to have a polynomial type, then I need to represent the coefficients, and I need to represent the degree. So coefficients I can naturally represent by a vector, and degree by another data member. So I have again the polynomial intended polynomial class. Here I've shortcut on the discussion. I'm just directly going into the basic representation. The class poly parameterized by t, where the coefficient is a vector of t, and degree deg is a variable of size t. So, and this is the assertion that I have. This is the property that must that should satisfy, not must, that should satisfy, is degree should be coefficient dot size minus 1, but not necessarily. I can say that degree is less than equal to coefficient size minus 1, because coefficient array must be as large. Now, coming to operations, let us just keep things simple. Let us define 3 operations. One is I can negate a polynomial, that I can negate a, which means negating each and every coefficient. So I have the negative of the polynomial. And given 2 polynomials, I can add them. So they are component-wise addition. Mind you, the polynomials are not guaranteed to have the same degree, so that has to be taken care of. That's what is expressed in this expression, which all of you know. Naturally, if you have negation and addition, you have subtraction as well. Right? So 3 basic operations. So with that, the specification of the polynomial t should support construction, destruction, copy operation, preserving sign, negate, binary arithmetic of add and subtract. For simplicity, I've not included multiplication and division because polynomial division particularly is a relatively complex operation. But our idea is not to write complex algorithms, but our idea is to develop designs and implementations and tests in a structured way according to the engineering practices. So just to keep it simple, I've just defined add and subtract. If I have add and subtract, then I have advanced assignment operations for add and subtract. And a special operation for polynomial is to evaluate. And this is what I want to do. I do not want a eval member function. So that if I have x of type t and I have p of type poly t, then I do not want to do p dot eval x to evaluate the polynomial. Rather, I want to overload the function call operator so that I can simply say px the way you write it in algebra. Right? You write px, the value of, so p2 is the value of the polynomial at 2. So I should be able to write that, and that is what you'll have to realize. So in addition, you have IO operations, read, write, of course. Task you have understood is the same. You have to design the interface. Based on this, you have to list out the signatures of different non-static and static member functions, friend functions, and so on. Support functions if you require any. Then implement, write all the function codes, and then write pass and fail tests for the polynomials. Okay. Clear? Any questions? No. Good.
Sir, in all the three cases, how would we write tests? I mean, in what format should we write the tests? I mean?
Test is a function where you are creating objects of different types and doing all the different operations that you have defined for that type.
Okay, just a function. All right.
Yeah, it's a function, and the mail call this test.
Okay.
Okay, what I'll do, for fraction, I will just include a small sample of a test function, right? In case you have difficulties. Yeah, there was another question.
What is meant by this fail test?
What is meant by
Fail test.
fail test? Is something which is guaranteed. Which is expected to fail. See, you can have failure of two ways. One is what is supposed to be successful fails to be successful, is a failure. And this is called a positive side. The other is something which is guaranteed to be negative, fail, unsuccessful, become successful, is also a failure. So pass tests checks for everything that should pass. Fail test checks for everything that should fail. So passing a fail test is to guarantee that wherever it should fail and give a proper message, it does so. Is that
Yes, sir.
Does that make sense? Okay. So after having done these three different utilities, your final part of the task is to play around with them, mixing. So now you already have the three types. You have a fraction type, which can take any integral type parameter. You have a polynomial type, which can take any numerical type parameter. So using that, fraction you have tested with int, poly you have tested with int n you have tested with n is equal to 4. But now can you test a fraction of int n or a fraction of int 4? A poly of int n, a poly of fraction of int n. Right? So that is what you can do in terms of your built-in types, that you can play around with them, mix around with them in whatever way you want, as long as it's mathematically or logically sensible to do it. Right? So here you write tests for mixing them around and check. So this will be a very strong test that when you mix them around, do they really? So when you have written the fraction class, you have made several assumptions tacitly about the type parameter t. So your int n class, int n type created must satisfy those parameters. For example, if int n does not have a multiplication, then fraction int n cannot compile, because fraction int n will need to do GCD, even if you forget about the multiplication of fraction, but it has to do GCD to be able to define a fraction. So int n must have that properly done. And if all these are proper, then this test will run very nicely. So this is your third assignment. You have a week for doing this, because this is pretty simple, particularly at the level at which you have now got skilled in C++ after Professor Shorangshu's lecture on it. So I mean, actually, Moodle entry and all that Professor Shorangshu will help me create. But let me know. I will send it across so that you have this presentation as a reference of what the assignment is. But at this point, if you have any question, just feel free to ask me.
Sir, we have to type it and submit, right?
Type it means?
Means typed code, right? Or handwritten code, like.
How can you do handwritten code that compiles?
In the last assignment, we were told to first type it and then write it down on paper. So.
I told that.
Like.
Maybe that was some misunderstanding. It is when you are solving some problem and all that, we ask for handwritten documents. But codes, you cannot do that. Right? How can we have handwritten code? And this will be a couple of 100 lines of code. If you handwrite, you will obviously make 10 mistakes. No, it has to be because in terms of the reason is simple. Do not think that we are just kind of parochial about all this. Is that certainly we want to make sure that your credit is not unduly taken away by your dear friend who makes free copies of what you submit. So if it's a general text, then it's very difficult for us to compare two texts. So we insist that it should be handwritten, because if you are handwriting the code, handwriting the answer, then certainly it is that much of extra effort, right? So the motivation to copy goes down, because electronic things can just be copied. When it comes to code, we really do not care, because we have code copy checkers. Those are very, very efficient. So we can do all possible checks between all possible submissions that you make, and figure out not only whose is a copy of whose and in which order the copies have been made. So we run those checkers, and copies made, our task gets less, because both of them get 0 and we don't have to wait. Right? So that's the basic rationale behind saying this. But
okay,
in terms of that's the reason I have also said that we do not need a documentation. I do not want you to write tens of codes, separate code, but put good comments, because most of the time, particularly in this kind of simple examples, the code comments should give you a very clear idea of what's happening, and you should learn to write good comments. Learning a lot is not good comment. Not writing anything is not good comment, of course. But writing the appropriate phrase of couple of words at appropriate points is what is needed. You should also practice that. That is one of the key areas of good software engineering practice. Any further questions? Otherwise, we are already past.
How much time will we get for this assignment?
You get a week. By next Wednesday. This is an easy one. It's not. I mean, doing the first one will take some effort, because these are all very similar. The first one, you have to create the structure, think about how to do this, how to write the tests, and so on. But once you have done one, then rest of it would be pretty straightforward, because as such the function member function bodies that you'll have to write are very simple, and also the arithmetic involved there I have already explained. So because we want to move on, I would next like to take you through a little bit more non-mathematical example of a little bit more elaborate design problem, and see how the design refinement, how the different stages of specification, design, implementation, test, these 4 basic stages which you are getting exposed to in this assignment, how will it play around when the problem becomes a little bit more complex. Then we go to a little bit more complexity. Right? I will tell the theory. Don't worry. I'll tell you the theory so that you can blabber the theory wherever required. But the theory does not help. It is a practice that helps. So that's a basic approach that I'm trying to take. Okay. So if there are no further questions, let us close. Right? Okay. Thank you very much. And as Professor Shorangshu has said, tomorrow he has certain parts left out from his C++ discussion, so he will continue on that. So he'll take the class tomorrow. Bye.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.
Thank you, sir.
Excuse me, sir.
Thank you, sir.
Thank you.
Yes.
Sir, when do we have the next test?
Yeah, so I think Professor PPD dropped off for some reason. So the next test, there is a designated window. If you see the website, we have given the date. It is there also in the like in the academic calendar. I think it's April 13th or something like that. I don't remember the exact date, but.
So, sir, we will directly have our end sems. There are no tests in between.
So there may be class tests. Surprise class tests may be there. Professor PPD will decide that.
Sir, actually, the institute has mandated coming offline now. So what if somebody misses those tests due to traveling?
No, this is a transition period, right? It is happening now only. So this week it will be over, right? All this traveling and everything.
Sir, actually, many students are still home, and so I don't think everybody will be on campus by this week.
Yeah, we'll see. We'll see how that works. Yeah.
Sir, they have asked us to reach by 31st March.
Okay, yeah, so fine. If somebody is traveling and missing classes, they are missing it. I mean, so try to travel during the weekend or something. I mean, I don't know really what will happen. Yeah. Try not to miss classes because the classes will continue. Okay.
And so tomorrow's class is online, right?
Tomorrow's class is online. Yeah.
Also, sir, do we have a lab class today?
Yes, we do have a lab class. Yes. Okay then. Okay. Thank you, everyone.
Thank you, sir.
Thank you.
So please stop recording.